So, very pleased now to start our session 6, which is of immense importance in TERN. That's ecosystem monitoring, assessments and reporting. And I'm very pleased to be able to welcome here Tim Clancy, who's an honorary fellow of TERN and who spent considerable years as TERN's director before me. So Tim, my friend, come up.
Thanks, Beryl. I won't say much, but I did want to just make the point. I think this is a nice progression from some of the previous talks where we're getting into the monitoring of system change and that. And I think it's really important as this is an area where the research infrastructure is directly connecting with the end users of the research, because most of the problems we're facing relate to global change type issues, and I think TERN's playing a really big role in this. So we've got a really broad range and a lot of speakers want to get through and have some discussion at the end about how it comes together. Should recognise that, it's not just local. We've got people from international, so TERN is linked into international networks, and that's another important thing, I suppose, of linking research into the bigger picture stuff, because I think most of these challenges are global challenges. So we'll move to the first speaker.
Good morning, everyone. This morning, I'm going to give an overview of an initiative we're working on in CSIRO called AusCalVal. Just a team of a couple of us within CSIRO, myself and Matt Garthwaite, who's also here today. We're also supported by a team from Frontier SI and Symbiosis Comms to get this initiative off the ground. Not anything anybody here probably doesn't already know, but a bit of context setting. Australia's big, one of the largest exclusive economic zones in the world of incredibly varying climate and environments. And satellite Earth observation data is extremely useful and heavily used to help understand and manage that environment. Quite a lot of the presentations of work we've seen have used remote sensing or satellite remote sensing data in some way. So quite prolific users of satellite EO data in Australia, but despite this, we don't actually have any satellites of our own that we've put up there. So we're entirely dependent on international partners for supply of that data. And a big part of the use of any data set really is quality assurance. There's been and currently step changes in the amount of satellite Earth observation satellites being launched, both by the traditional old space, international space agencies, but also new space in the commercial sector. There's huge amounts of satellites going up, which means a huge wealth of data. Quality assurance then is really important, so we know the precision and accuracy of the data we're using, but also so we can compare between sensors and from the same sensor over time. And a big part of that quality assurance piece is calibration and validation, which is where AusCalVal comes in, and recognising that Australian scientists have built really strong expertise and reputation for CalVal using Australia's environment and southern position strategically to contribute to international science satellite missions. An example of TERN infrastructure that's used in this way is the Tumbarumba site there that Will Woodgate presented on yesterday. Recognising that an investment is needed in an area where we get so much benefit from in Australia, the Australian Space Agency released a roadmap in 2021 and 5 focus areas, including data quality assurance and integrity monitoring, which is where AusCalVal fits. And drawn out of that, some relevant objectives and outcomes being a holistic marketable capability that allows international partners and Australian missions to certify their EO data as meeting spatial, spectral, and radiometric quality standards, with an outcome that calibration and validation sites, facilities, systems, personnel, and expertise resident in Australia are widely used for international and Australian missions. Worth noting here that until recently, the Space Agency's route to deliver on this roadmap was a program called the National Space Mission for Earth Observation, which included AusCalVal as a concept, but also the actual launch and design of satellites. That was recently cancelled, unfortunately, as the government didn't want to follow that strategy to invest in space and Earth observation. Despite this, the concept of AusCalVal in various guises existed before that program came along, and support for it continues. So we started in SARO implementing it in 2022, and we're persevering beyond the National Space Mission. Alongside the roadmap in 2021, a report was published by Frontier SI that outlined the high-level concept for what a centralized facility that supports and coordinates EO-CalVal capability in Australia would look like. That identified 25 sites or networks that constituted what Australia did in the area, and it's really what we're using as a blueprint for how we've set up and started to implement what we're doing. Of those 25 things, the existing ones are spread across a lot of different organisations. So a key part of what we're trying to do is link all that up, and I think in Andrew's opening remarks yesterday, he talked about strategic national assets. I think that's something we want to recognise in the capabilities we have here and really collect that together and present it as a strategic national asset. Likewise, this morning, Bronwyn was talking about achieving alignment, and again, that's I guess a theme that we're working on here to try and align all the different domains, different organisations under one EO-CalVal subject. And yeah, I think the foundational capabilities and sovereign capabilities part of her discussion this morning really resonated with what we're trying to do. In TERN, there's a lot of this work that already happens, and I think in the previous slide, I forgot to mention the specific sites that the TERN ones that were highlighted are the Odds Flux Network, the TERN Super Sites, and the Cosmos Soil Moisture Network. And a lot of work has already been going on, working with international space agencies, supporting EO missions. Some examples, there's been support to NASA since 2015, with data for SMAP, which is the Soil Moisture Active Passive Mission, JEDI, which was mentioned a couple of times yesterday. Will talked about that with respect to Tumbarumba, EcoStress, which is a thermal imaging mission, and in the future, NISA's a synthetic aperture array radar that I think there's some work going on. GBOV, another one that was mentioned yesterday, and also forest biomass, supporting a initiative called GeoTrees. In terms of collaboration, we really just want to see more of this happening. So we see ourselves providing a facilitation role and coordination to link up all the expertise with initiatives and increase engagement. So really, in summary, as what we want trying to achieve is support and promote Australian Earth observation, calibration, validation activities, and infrastructure as a coordinated national capability, facilitating free and open access to data sets, and quality assured and consistent data and resources through a single interface. Over the next 12 months, some of the activities we're working on are a centralised information portal on capabilities and activities with the CalVal applications within Australia, which is really that access piece and identification. I think there was talk yesterday about part of the challenge is, well, a big part of the challenge is knowing what's available. And there's a data hub for hosting distribution of data, so making data available or pointing to where it is in the situations like TERN. In the discovery portal, representing the community to seek funding in the absence of a national space mission. It's trying to get funding to sustain what's there and new capabilities, and then trying to develop a framework for how we present that consistently, being a cross-domain sort of thing. There's it's all really good work, but there's a lot of different ways of presenting the information and quality indicators. Fundamentally, we're trying to draw on the expertise that's there and the community that's there, so we're very open to questions, ideas and suggestions. So please feel free to reach out to myself or Matt if you've got anything you want to talk about. Thanks, everyone.
Right, so I'm Patrick Baker. I'm from the University of Melbourne. I'm going to talk today about the Starvation Creek Forest Dynamics plot, a large-scale forest dynamics plot that we've recently established in Victoria. I'd like to begin by acknowledging the Wurundjeri people, the land on which the plot and the work has been done, and pay my respects to their elders past, present, and emerging. The title of the talk is ForestGEO Comes to Australia. So for a bit of context, some of you may know about ForestGEO, some of you may not. ForestGEO is the Forest Global Earth Observatory. It's a global network of large-scale, long-term forest dynamics plots that's coordinated by the Smithsonian Institution in the US. This is a map of the 75 plots in the network. Just as a little bit of background to sort of motivate why I'm giving the talk, the ForestGEO plot was established in 1981 with a large plot in Panama. A population ecologist, Steve Hubble, who was then at Princeton University, was getting interested in the question of why are there so many tropical tree species? Why does a community in the tropics have so many species? Why doesn't one species take over and eliminate the rest? And as a population ecologist, he really felt that a key to answering that question was understanding the demographics of the populations of each of the species within a community. However, the inventory sort of infrastructure in the tropical forests of the world was very inadequate for answering that question. It had been, European foresters had established small plots, sample sizes for most species of n equals 1 or 2, and just not possible to derive demographic parameter estimates of recruitment, of growth, of mortality from those plots. So he had, I suppose in retrospect, the obvious idea of just making a much bigger plot. And so with Robin Foster, a botanist at the Field Museum in Chicago, they set up a 50-hectare plot in Panama at Barro Colorado Island. The initial census, which was completed in 1981, had 200,000 trees in it across 300 species. And this really effectively recalibrated how we thought about how to do science in the tropics. It changed the scale of our ambitions in many ways and revealed all sorts of interesting things about how forests work. That led to a rapid establishment of other plots around across the tropics. By the 2000s, we were seeing plots extending into the temperate zones. And by 2019-20, this was the map of the network. And for this audience, obviously, you will have noticed in the moments that I've been talking here, there's a glaring omission, and that would be in the bottom right-hand corner. For some fortuitous circumstances, we wound up in a position at the end of COVID to establish a ForestGEO plot in Victoria. And so we have established the plot just there east of Melbourne at a place called Starvation Creek. So the plot is in what we call low elevation mixed species forest. So this is a forest type that is common across southeastern Australia, Tasmania, Victoria, New South Wales. This is a picture of the forest from the back side of the plot, eucalypt overstory, sort of shrubby small trees in the understory. In this case, a fair few tree ferns there as well. So the strength of the ForestGEO network was that the plots were all established using the exact same protocols, right? And the plots were big. So in the tropics, because you have so many species and you wanted to get decent sample sizes for as many of them as possible, the plots usually were 24 to 50 hectares. As we moved into the temperate zone, they were smaller because we didn't have as many species, so more often 16 to 24 hectares. Our plot at Starvation Creek is 16 hectares, so it's 400 meters by 400 meters. Every tree in that plot that's greater than 1 centimeter in diameter at breast height, so approximately the size of my small finger here, is measured for DBH. It's identified to species. A paint stripe is put at the point of measure so we can return to it in 5 years. We measure these every 5 years. A unique identifying tag is put on, either wired on or nailed on, depending on the size of the tree. And then the tree is mapped to the plot coordinates. We began by putting in a big professional survey on a 20 by 20 meter grid. So we have 441 monumented corner posts across the plot, which is very good for taking students into the plot who easily get lost. It's easy to find where you are when every 20 meters there's something to tell you where you are. This is a digital elevation model, the shading there, and we were very lucky in the location here. We have a lot of topographic variability. So we've got a hill up here at the top, the lighter color, and then 2 gullies there and there. We've got all north, south, east, and west aspects. We've got a ridge that runs down the middle of the plot. So there's a lot of topographic variability in there of interest. The first tree we measured was the little Paltanea muelleriana there in the top left. We did that in early December 2021. The last tree we measured is this big mountain gray gum, Eucalyptus ipelicarpa, which we measured at the end of March this year. So it took about 16 months to do all this work. And I'm going to just run through some of the sort of early results that we have, just mostly descriptive stuff for you, so you get a sense for what this plot is about. So this is a map of every one of the trees in the plot. So there's 51,324 trees that were mapped in the plot. You'll notice it says there's 58,242 stems. We had a lot of trees, or well, we had 7,000 trees that forked below the point of measure. So each stem gets its own tag, but each tree is recognized as an individual. Across those 51,000 stems, we had 47 species of woody plants that reached 1 centimeter in diameter. The most abundant species was Leptospermum continentale. We had 17,560 individuals, many of which, many of which are in this super, super dense clump. So the density in here is about 15,000 trees per hectare, which was a bit of a nightmare, to be honest. We also had 15 species with less than 10 individuals, and we had 2 species that only had 1 individual each. So we had the full gamut of abundance, from 17,500 to 1 individual. The biggest tree that we had was just under 2 meters in diameter, and we had a fair bit of congeneric diversity in the plot. So we had 7 acacia species. We had 3 species each of Cassia, Paltanea, and Olearia. But the thing that really sort of stood out was that we have 13 eucalyptus species in this forest. And that's, on the one hand, remarkable, although it's pretty common in southeastern Australian forests. But in many ways, it sort of harkens back to Steve Hubbell's original question of how do you have so many tree species that coexist in forests? In the Australian context, the obvious question is, how do you have so many eucalypts that coexist in the forest? They're all doing the same thing. They're all canopy trees. They're big and tall. Why doesn't one eucalypt just rule them all and competitively exclude the others? So I'll give you a couple more examples of some of the data. These are the 2 most common eucalypts in the plot, Eucalyptus obliqua, mesmate, and Eucalyptus seabrai, silvertop ash. And you can see the distribution of the seabrai is very tightly associated with the hilltop and the ridge, and it actually has almost a discrete boundary when it hits the mid-slope site. So very, very specific distribution within the plot. Whereas the obliqua is a little bit more cosmopolitan in its distribution, less abundant on the ridges, but probably because there's so much silvertop in there, and certainly more abundant in the gullies. Probably the most distinct topographic affinity, though, is from the tree ferns, which are very, very tightly associated with the gully system in this plot. The other thing that was of interest when we started looking at the data, this is a map of all the trees that are over 50 centimeters in diameter, all of which are eucalypts. There aren't any trees that aren't eucalypts over about 35 centimeters in diameter. And what's remarkable about this is the incredible uniformity of the distribution of large trees. So we have 400 20 by 20 meter quadrats within the plot. That's just how it's organized. Of those 400, 379, so 95% of the quadrats have at least 1 individual that's over 50 centimeters in diameter. And half of them have an individual that's over 75 centimeters in diameter. So that has obvious implications in terms of thinking about spatial distributions of biomass and carbon within these plots. The plot itself is a significant piece of research infrastructure, even though it doesn't have little lights that ping and things that make noises on it. But we've also put in a sort of research infrastructure and instrumentation on top of the plot. My colleague at the University of Melbourne, Andrew Western, a hydrologist, has put in a network of soil moisture probes or soil moisture sensors that we have sort of 8 different measurements through the top meter of the soil across the plot. Darius Calviner has putting in 3 of his leaf scanners, so those will be permanently in place and monitoring every day for the foreseeable future. We have a network of acoustic monitors that are going into the plot, and we have a telecommunications gateway that helps move all this stuff up into the cloud. One of the nice things about the plot is it has very good telecommunications access. So when we were establishing it, we had students who would be working during the day, and if they had a lecture on, they would just stop, go get their computer, sit down on a log, zoom into their lecture, and then when the lecture was done, they would continue working, which was fantastically convenient. This is my gratuitous animal photograph. I'm a tree person. We have a bunch of other supplementary stuff that's going on, so camera trapping. So Matt Luskin and I are talking about the wild obs stuff, which is great. You'll notice this big brush-tailed possum. If you look carefully, there's a feral cat behind it on the right-hand side. Apparently the cat didn't want to tangle with the possum. We have phenological monitoring that's going on of all the eucalypts, and we're thinking of expanding that to the other species as well. We'll be doing annual mortality assessments to look at interannual variability in demographics and its association or not with climate. And we'll be doing annual terrestrial laser scanning with a higher resolution scanner at the center of each of the 16 hectares in the plot, and we'll repeat that each year. Don't ask me any questions because that comes later. This is just a bit of a sense for every tree with a painted stripe on it has had its hands on, someone's put their hands on it, and hopefully we'll be there again in 5 years. Thank you.
My name is Zach Brown, and I'm the manager of the Australian Mountain Research Facility. I would first like to acknowledge the traditional inhabitants of the lands on which I live, work, and play. The research carried out with this project takes place in mountains of great importance to Indigenous peoples. I pay my respect to these peoples, past, present, and emerging. Additionally, I'd like to acknowledge the efforts of volunteers, conservation officers, and academics. This facility would not be what it is without the time, energy, and hard work of all involved. I've included a little asterisk next to my name here because to properly acknowledge all people individually would probably take the duration of my time slot. The Australian high country contains immense cultural, economic, and biological value. It's been used for tens of thousands of years by Indigenous peoples for harvesting bogong moths and for ceremony. Covering less than 0.5% of Australia's land area, it still yields approximately 9,600 gigaliters of water per year, equivalent to about 29% of the average annual surface yield of the Murray-Darling Basin. The use of the Alps for recreation brings approximately 2.5 million visitors per year, providing employment and diversification for regional communities valued at about $7.7 billion. And finally, the ecological value. It's a hotspot containing a variety of endemic species that are incredible on their own, but also contribute to the ecosystem services from this bioregion. Yet despite that, it's underrepresented in long-term observations. Alpine plants and soils are sensitive to climate change due to dependence on snow, cool climate, and reliable water presence. In Australia, low elevation mountains have limited capacity for vertical species movement to cooler niches. The Australian Mountain Research Facility is an ARC linkage LEAF grant funded in 2019. It was led by Adrian Jokotola as well as a team of researchers across Southeast Australia. And it was done in partnership with various agencies in New South Wales. And the aim of this was to improve the predictive capacity around biophysical and biological feedbacks by providing unified observational and experimental infrastructure. And that was all done in order to support research projects which would inform and improve management strategies. As you can see from the map on the right, each of these white circles indicates where we have a permanent monitoring plot. And so those are located in ACT, New South Wales, Victoria, and Tasmania. Some of our sites are located above the tree line, such as the image on the left, while most of our sites are located below the tree line, such as the image on the right. In any case, each site contains a 1 hectare plot, inside of which the vegetation dominating is grasses, herbs, and some shrubs. That plot is located on a slope, which terminates in either a bog or a stream or both. And contained within that 1 hectare area, we have a variety of micrometeorological sensors, such as radiation, wind, air temperature, rainfall, snow depth, and a few of our sites also collected ecovariance measurements. Additionally, throughout that 1 hectare area, we have some subsurface measurements, such as piezometers and soil sensors. And those are scattered around from the top through to the bottom. And each of these plots is surveyed through the TERN AusPlots protocol, which characterizes the soil and vegetation. In addition to that, we also carry out water chemistry measurements and do geomorphology surveys. Pictured here is a diagram representing one of the subsurface surveys we carried out. And this was done at the aqueduct site, pictured on the left. So essentially, within the 1 hectare area, we created a grid, and at many, many points along that grid, we stuck a long metal rod into the ground until we hit bedrock. And essentially, that gave us an indication of how deep the soil was at any point. And geomorphologists use that to essentially predict where the water table will be, and we confirm that using piezometers. We're hoping to use this to help inform plant and soil responses as soils dry out or they experience various precipitation events. Another topic our research group is involved in is the status of snow gums in the mountains. So as you can see here, there's a massive dieback event occurring in the mountains in which trees are being absolutely devastated by this native wood-boring beetle species, Phoracantha mastersii. So pictured here is an adult emerging from some bark under the tree, and this pregnant females essentially lay their eggs in the sapwood of the tree. The larvae, when they hatch, they eat their way through the sapwood, creating these feeding galleries, which you can see on the left. And those feeding galleries result in the total hydraulic failure of the trees, eventually leading to the tree death. It's entirely unclear what a widespread and rapid loss of snow gums will have on the Australian Alps. The trees dominate the high country canopy, and land surface within a healthy canopy has been found to have a deeper snowpack and for a longer duration compared to unforested land. Additionally, snow gum leaves can physically capture airborne mist, improving landscape water inputs. Consequently, loss of trees could dramatically alter the hydrological dynamics of the mountains. The Save Our Snow Gums project will complement the AMRIF network with snow gum woodland sites. So we'll have long-term forest monitoring plots. We'll augment those with subsurface water dynamic sensors such as piezometers and soil moisture probes. And we'll measure carbon dynamics, mainly pools and fluxes using chambers, as well as a new snow gum flux tower installed in November 2023. In addition to all the observational equipment I've described already, we also have a variety of experimental infrastructure, such as the deployable heat wave chambers, which utilize active and passive heating to warm a short stature vegetation community for up to 7 days, as well as the distributed rainout shelter experiment as part of the DroughtNet network. And at one of our sites, we have the Future Clim experiment, which manipulates both warming and precipitation in a full factorial design. We're going to maintain a long-term research presence in the mountains, and we want to continue to engage with conservation officers as we really value their input. And most of our data are publicly available at amrif.org, so please, I encourage you to go check it out. We really want our data to be used, so you can download whatever you want. And if you can't find it there, then please contact us and we can discuss how to move forward. Thanks.
Good morning. My name's Rob Hassett. I'm with the Queensland Department of Agriculture and Fisheries, and today I'll talk to you about the Land Condition Assessment Tool. I'm going to bring this down a notch or a dozen from the very scientific, spectacular work that's been presented so far. This is more about a practical way of capturing a lot of data and engaging with landholders and people that don't have the skills and experience that a lot of you have. I'd firstly like to acknowledge the First Nations people. Also, I've got the old name there, but DECU funded the development and implementation of this tool. The support of my fantastic team led by Kev McCosker, many users around the state of the tool, and TERN for this opportunity. So when we talk about land condition, there's lots of different definitions depending on your focus. So it's land condition, it's a point in time, the condition at that point in time, not land capability. So depending on the purpose or the focus of the work you're doing, say for example grazing land management, there's a productivity focus, vegetation, biodiversity, and stability, landscape stability, different focuses. But one of the things that we know, regardless of the purpose, we know that changes in condition can have significant impacts across a range of environmental and social areas. So condition can be slow and incremental to increase, and it can also decrease quite rapidly. What LCAT is seeking to do is make land condition assessment and the capture of data a lot more accessible to a much greater group of people, I suppose. And it considers all of the indicators and the different definitions, and it does that by calibrating the same input data set, calibrating it different ways to produce immediate results. So the reason why I developed that was quite a few reasons, but largely in 2014 the Reef Plan report identified a range of gaps and issues with the paddock to reef data that was being collected. But that next one down there, the awareness, learning, capability and capacity building. I've been very fortunate for 35 years, been collecting data across pretty much all of Australia. And for 17 years, it was more of a lifestyle than a job. I was away so much. So those opportunities don't exist anymore to have that kind of ability to pretty much go anywhere. I had free license to go anywhere. So as I've gotten older, a key thing for me, a key motivator for me, despite the other uses, is that getting that capacity and capability, but also giving people that cover, grazing is the largest land use in Queensland and mostly across Australia as well. So they're the people that we need to be engaging with to help us manage the lands. So in designing the tool, I designed it in 2014, and one of the motivators was for me to use it as well. I haven't used paper in the field since 1996, I think. And I've developed different methods over the years, with lists and stuff that you've got to read electronically, and it can be a pain. So I wanted to have something that was quick and easy to use. It's not a quantitative assessment, it's about capturing a minimum set of data that's good enough to have confidence in what we're looking at, but be able to collect more data. My focus is, I've done a lot of quantitative transect stuff, but my focus has largely been around volume of data, capturing a lot of data in a short time to get that snapshot in time over a big area. And a big issue was capability and capacity. So have results generated by the tool in the paddock so that people could look at the result and start learning from the changes that they might see at the next site. And it's complementary. It doesn't replace anything. It's just another tool in the toolbox. And it set a standard for assessment. So it standardised the assessment capture. It's a science-based framework, so it draws on a range of inputs from a lot of published literature and also things that I've developed over the years. And what makes it accessible is turning those scientific concepts into pictograms. I've worked with landholders whose fingers have been as big as my elbow, and they don't want to be scrolling through lists and things like that. So just being able to tap on pictograms that represent scientific values is much easier. So it uses a framework of a bunch of land condition components, and each of those components has a set of long-term land condition indicators. And the advanced version is just more data rich. It's capturing a lot more information about species and erosion processes and things like that. And what it does is it generates 15 immediate in-field results. Offline, you don't need phone reception, so you get all of the data for analysis, you get the results for that learning ability. And the first set of results there you can see has got that grazing productivity sort of focus, so that we can engage with landholders and get them thinking about how to manage their business, but also in a way that is not impacting the environment. And then there's another set of results around environmental or landscape components. It's important there that I've got indicative landscape stability, indicative riparian zone, natural capital carbon store. It's not a quantitative method, but it's a fairly good indicator of the potential that you may have with that land. It's used in Survey 123 Field App. It's standardised. There's 1,400 categorised plant species, and the way we can generate different results, for example, there's 585 pasture species, and each species has actually got 6 different values that allow it to input into different results. Here's an example up in the Burdekin catchment. You can see a fairly normal site or natural site, but it's close to a riparian area where there's no infrastructure. So it's a matter of, these are just screenshots from each page. It's a matter of just tapping on the pictograms as you move through and generating that suite of in-field results. And you can see there for the grazing side of things, we're in C conditions, so it's not that great. There's erosion hazards, there's water quality hazards. You can see down the bottom there, the riparian zone stability's not good. But the landscape stability and those other results are sort of, they're better than the productivity result might indicate. So another way of looking at that is, we've got having the different results can mean different things for people, but also give us ideas of how we can assess or value different data that we have. So does one site have more capacity to recover than another? Do we need to be thinking about different land use, current land use and land use change? So in each of these sites, up at Cape York in the Brigalow Belt in central Queensland, up in the Burdekin catchment, each of these sites for grazing are in C condition, so poor condition. And they've got slightly different drivers, excuse me. Some are around pasture, the dominant pasture species, some are around the dominant pasture density. The understory density in the second photo there, the Brigalow regrowth, that's impacting the productivity of that site. However, 2 of the 3 of those sites are actually pretty stable. They're not going anywhere. So perhaps that middle site where there's that regrowth, perhaps that's a better opportunity for letting that regrowth occur, and it's a nice stable site. The site on the left, on the right, obviously got a big gully coming through it, so that's got a much greater water quality risk. And they're the kinds of things we're working with landholders, particularly in the Great Barrier Reef catchments, to understand the impacts of their management and working with them to try and address those impacts and have better outcomes, not only for their business, but for the environment. So I've called that the strengths of the simplicity of design and use. In retrospect, I probably should have called it the so what, because that's a response that a colleague gave to me a long time ago about all this data that was being collected, and we can collect the best data and we can make the best products and have the best reports, but ultimately, so what? And that really struck with me. So in 2.5 years, we've collected a bunch of data, largely focused around the reef catchments, because that's where a lot of the investment has been. But the so what comes down to that capability, capacity building, that engagement and awareness. If we can't get landholders and NRMs and people with less experience than yourselves, we need to get those people thinking about these issues. And the most simple way to do that is getting them engaged. So I haven't gone into data or anything like that. That link down the bottom right there, that's the first 2 years of data, just a high-level analysis. And encourage you to have a look. It's as I said, it's not a quantitative method, but there is a ton of data in there that can really give us some good insights into what's happening. Thank you.
Hi everyone, my name is Jokotola Omidiji. My presentation is titled Erosion Rates Reveal Tectonism Influences the Short and Long-Term Variability of the Rocky Coastline. Rock coasts are erosional landforms, and unlike sandy coasts, the morphologies of these coasts are difficult to attribute to a particular process because they are shaped by wave forces, weathering processes, geology, climate, tidal duration, ice, and tectonics. Therefore, understanding precisely how instantaneous erosional processes scale over millennial timescales is a major scientific quandary because changes to rock coasts are long reversible. In order to decipher erosional processes influencing rocky coastline changes, scientific efforts are focused more on the debate regarding the relative role of waves and weathering processes. A general assumption with no consensus is that as shore platforms fronting cliffs widen, there is a process shift from a dominance of wave-induced erosion to subaerial weathering processes. This work sheds new insights on 1. The debate about erosion process dominance from sites where active tectonics introduces more complexity to these debates, and 2. The common public misconception that earthquake-induced coastal uplift will suppress or eliminate long-term coastal hazards such as erosion, sea level rise, and flooding of low-lying development. 2 locations in New Zealand were studied. The first site is the Kautara Point on Maya Peninsula on the east coast of the North Island, New Zealand, where paleoseismic records indicate that the last uplift of 3.1 meters occurred between 1 and 300 years ago. This event lifted a wide expanse of seafloor into the intertidal zone. The second site is the Kaikoura Peninsula on the east coast of the South Island, which was uplifted by approximately 1 meter during a 7.8 magnitude earthquake in 2016. This caused the reshaping of the nearshore coastal environment by elevating all platforms and extending the width of some. Both sites are characterized by lithological units developed in mudstones, experience semi-diurnal microtidal conditions with mean spring tidal ranges less than 2 meters, possess platform gradients less than 1 degree. Intertidal platforms are formed within a similar elevational range. Using field data from the microerosion meter and photogrammetry data, we intend to answer 3 questions. 1. Do erosion rates and processes change after coseismic uplift using within site, pre and post uplift erosion data? 2. Are there differences in the erosion rates between uplifted coasts with similar lithology and uplift effect on tidal range? And 3. What are the implications of these rock responses to coastal evolution, to marine terrace erosion and earthquake reconstruction? Our key findings in relation to the research questions are: 1. Do erosion rates and processes change after coseismic uplift? Yes, it does. The MEM erosion data showed that the tectonic uplift temporarily accelerated erosion rates with mean surface vertical erosion rates of 2.25 millimeter per year for all platforms. This is a 104% increase from a pre-uplift rate of 1.10 millimeter per year. As a result of the uplift, subaerial weathering is causing a faster rock breakdown. Higher erosion rates during summer, which resulted in seasonal variations in erosion rates pre-uplift, have disappeared post-uplift due to inhospitable environments for algal cover. For research question 2, are there differences in erosion rates between uplifting coasts? At Kaikoura Point, The mean annual erosion rate is 1.97 millimeter per year. But unlike Kaikoura, there is currently no downwaring data to compare with in order to understand how the mudstones responded immediately after the uplift event. But what is interesting about these rates is that they are statistically similar to the post-uplift erosion rates at Kaikoura, which indicates a comparable pattern of rock response at both sites post-uplift due to the similar lithology and position of rocks within the tidal range. These rates imply a centennial scale response time for uplifted shore platforms at Mahia that would have implications for platform erosion timescales at Kaikoura. That is, if another uplift does not occur soon. But how are the implications of this results and of all of these rock responses on marine terrace erosion? The recorded higher erosion rates after uplift means that uplifted terraces and shore platforms at Kaikoura, which is shown in picture A, that are currently beyond platforms that are currently beyond the reach of waves and tides, can rapidly be removed by post-uplift erosion, as shown on picture B, which is the Maya site. At the Maya site, there is continued effect of marine processes directly on the cliff dome. Our results demonstrate that existing conceptual models and numerical models of shore platform evolution or cliff erosion that suggest unchanged erosion rates after an uplift can be improved by taking into account empirical data collected in the field before and after an earthquake. The results from this study also shows that if the period between earthquake is long enough, rock breakdown and marine processes could remove any evidence of an earthquake terrace, which we think is evident from terrace reconstruction studies at Mahia Peninsula. Because the shore platform is so wide, we have concluded that it is as a result of two earthquake event sequences. In summary, contrary to the misconception that earthquake-induced coastal uplift eliminates long-term coastal hazards, we show that uplift induces faster erosion, and therefore there is a need for continuous monitoring and identification of sustainable coastal management strategies for all coasts, be it sandy or rocky coasts. Thank you. Thanks for listening.
Yeah, good morning. Good morning, everyone. My name is Jeongsoo Park. I'm from NIE, South Korea, and I'm in National Institute of Ecology in South Korea. I'm in charge of KLTL. I'm glad to be able to introduce the KLTL and our new plan for the ecological observatory. I divided my presentation into two subjects. First one is about KLTR, and second, the plan for the ecological observatory network in Korea. First of all, I'd like to introduce the history of KLTR. This project was started in 2004. Diverse ecological research was conducted by academic groups and accomplished lots of things. From 2014, we are more focused on ecosystem function study and field study-based research conducted by NIE. Starting 2024, we plan to set up automatic observatory to collect standardized ecoclimate data. Yeah, this slide shows the KLTR site and the research subject conducted right now. Study site of KLTR located across the country. Especially, we have 4 main sites, Mountain Jeonbong and Namsan in Seoul, and Mountain Jiri and Halla Mountain in Jeju Island. Field research subject was categorized into 8 parts. For example, carbon cycle, species population dynamics, phenology, and the drought experiment, and so on. One of the most important research topic is carbon cycle conducted in Mountain Jeonbong. We have measured air covariance and tree biomass changes and soil respirations. And furthermore, we monitoring the amount of carbon discharge from forest to stream using Brinoch system. It is the only one whole carbon cycle monitoring system in South Korea. We try to expand this system into other sites. This graph shows the carbon dioxide flux changed by hourly and by seasonally in Mountain Jambong. The dominant species in Mountain Jambong is Quercus mongolica, and which is almost 10 years old forest. In the left graph, when we compare the variation of the carbon dioxide by hourly between summer and autumn, carbon dioxide flux changed dramatically in summer because of the photosynthesis of trees. Finally, we calculated 1.5 kilogram carbon dioxide was observed in Mountain Jambong forest from April to October, which is similar to the carbon sink in European broadleaf forest. Next, I will introduce our plan for the National Ecological Observatory Network. As you know, TERN and NEON in US already have the automatic ecological observatory network and produced diverse ecoclimate data to respond to climate changes. We also have planned to the National Ecological Observatory system. This is a blueprint of our super site. We can collect the ecological data in the air, for example, radiations, carbon dioxide, carbon concentrations, and range of meteorological data. And we will measure water qualities and carbon discharge through the system. And in the soil, we will soil respiration and the soil property will be checked. KLTR site will be combined with automatic observatory systems, and we will be a nationwide ecological, and we will be the nationwide ecosystem observatory network to monitor the ecosystem changes and produce standardized ecoclimate data. NIE already have a nationwide ecosystem monitoring data, which is conducted since 1980s. This data will be integrated with time series data generated at our ecosystem observatories. This allows us to more accurately predict the response of the ecosystem across the country. There are three kinds of observatory. First one is integrated ecological observatory named SuperSite. In this site, we will measure the meteorological factors, remote sensing, carbon cycle, hydrological factors, and soil property, etc. Additionally, we will draw vegetation point map and detail topographical variation within the 16-hectare forest according to the ForestGEO protocols. Second, we will have 3 local sites depending on the ecosystem type, such as wetland, urban ecosystem, and Gochawal. Especially Gochawal is a unique ecosystem located in Jeju Island. It is known as vulnerable to climate changes. Lastly, mobile deployment platform, MDP, it will take action in the urgent ecological issue, likewise outbreak of insect, wildfire, and the mass mortality of species. And this is timetable for the ecological observatory construction. We have planned to construct ecological observatory network from 2024 to 2027. The detailed plan and design will be start of next year, and the infrastructure construction is going to be started in 2025. We expect that this total budget might be 20 million Australian dollars. And we will select specific location for the super site based on their expertise opinions. First location is the mountain Gyeong, which is located in the temperate climate zones. Dominant vegetation is Crocus variabilis and Crocus mongolica. And the second location is Wando, which is warm temperate zone and has largest evergreen broadleaf forest inland of Korean Peninsula. Dominant species Crocus acuta and Camellia japonica. In case of local site, although it needs further discussion, we consider Daejeon for the urban ecosystem, Upo for the wetland, and Gochawal as a suitable site. Yeah. Furthermore, we started the project constructing integrated eco-climate data platform this year. We will combine the data from 6 different government agencies, for example, Ministry of Environment, the Ministry of Agriculture and Forest Service, etc. And new data from our ecosystem observatory will be added in this platform in near future. This slide shows the architecture of the ecoclimate information system. As mentioned above, we will collect ecoclimate data from 6 different government agency and make ecoclimate data repository system. And our climate observatory will be produced standardized time series data. This data is used to validate other data set and combined with the special data conducted by 6 different government agencies. We predict that the main user of this system is government and academic researchers rather than citizens. Last but not least, we will want to collaborate with other countries' ecological observatories. We will often provide standardized data to researchers across the world to detect ecosystem response to climate changes. This project cannot be accomplished without your help and require advanced experience. We believe that this effort will be the solution to the ecological crisis caused by human activities. Thank you very much.
Just pop. Yeah, okay. Good morning. I'm going to present the topic. I'm a PhD student at UTAS, improved monitoring of ecosystem using high-resolution remote sensing. This is my team, Arco, head of school at UTAS, Darren Turner at UTAS, and Teja Kateborn from Germany. I can see, well, anyway, why high resolution imagery? So as we know, US imagery helped to connect field plot survey to coarser spatial scale satellite data, and this is because of the specific characteristic. They have very high spatial resolution between 1 millimeters to 1 centimeters range pixel. Also, it allows you, it gives you more detail, but that means you can see, detect better the spatial variability in vegetation. And also, we give you high temporal resolution data acquisition that everyone is talking about. It will help to provide highly precise map in a temporal resolution, and we help to understand better the climate change, how they impact in ecosystems. It's also a good opportunity to derive this ecological, biophysical, and biochemical variables from UIS data. After Arco, we explain more about the data collection and processing that is being done with the UTAS team and TERN. And also, how I'm going to do it, I'm going to using advanced deep learning techniques to derive this ecosystem information from raw drone data, and by aiming basically to deliver automated workflow to assist in assessment of ecosystem health and helping to contribute to validation through this local scale to national scale through satellite data. So we know that science, technology has been progressing. So sensors, so we have a more spectral resolution, but also computation has been evolving, algorithms has been evolving too. So how it's been progressing? So right now we're more in the deep learning. It's not machine learning, it's the deep learning techniques. And what we're doing is so how we combine these new AI evolution with the combination with high resolution imagery. So this allows us kind of to help to extract valuable ecosystem information from these drone data for ecosystem science. And deep learning frameworks work like recipes. So in order to have a good output of this recipe, we need to have good ingredients. And when I say good ingredients, you need specific training data. So by that, so before we have image classification or regression algorithms that we use texture information, where the image classification is basically the assignment of a class to the entire image to detect the presence of the object. Then the algorithms advance, so we have the object detection recognition, where you will use bounding boxes, and that will allow you to localize the object, but not the shape. So this is why we end up with the segmentation algorithms, where it's based in pixel-wise annotation. And there are three types of segmentation that is using computer vision to partition that image into regions. And then we can apply semantic algorithms by assigning that label to each pixel in the scene, or the black image with the bounded boxes is instant segmentation that will allow you also to detect the individual object and count the object. And then you have the panoptic segmentation. That's a blending between semantic and instant segmentation. So why is it important? It's because they give you the ability to characterize more complex patterns with imagery data. They're very good at memorizing those patterns. Also, it retains the spatial information, spectral information. It has the ability to distill spatial features, but as I mentioned, this training data, texture, spectral signatures, corners, shapes. Also, they're pretty good to automate the feature engineering by predicting the most appropriate predictor for this vegetation analysis. That means you need less knowledge about the inputs that you give to your model, because the algorithms will give it the answer by itself. So this is the big picture of of our PhD project, based on mostly fractional vegetation cover, going through composition, structure, mostly in 3D representation, transferability of the models, and function more in a biochemical variable way that perhaps we'll be applying image hyperspectroscopy or hyperspectral data. And then we have the conclusions. So what is fractional cover? If not everyone knows, so why it's so important to measure, to map and monitor is basically the estimation of the relative subpixel proportion of photosynthetic, non-photosynthetic, and bare Earth. So this FVC can be used as a measure, so it can be translated into ecological, biophysical, chemical, plant properties at different spatial scales. In our case, we're going to be fixed on the local, not regional, global. Also good for mapping. It will be a proxy for the estimation of the vegetation cover. and it can be used in various fields and scales. Also, we have to monitor, the ABC measurement and the temporal variability can be used to detect these change analysis that we have in time. So the way we're going to do is using this RGB texture to spectral information that represent the spatial information and represent the distribution and differentiation of objects that have same spectrum. This is why we're using multispectral data. In this case, so this is the first chapter or second. So it's about improving this ABC mapping classification. We're trying to differentiate the similarities between NPV and VE by applying these deep CNN architectures where we're trying to exploit at maximum the spectral and spatial information. Where we use the RGB multispectral data. So why we're using is because this is a geophysical parameter that describes pretty well the ecosystem health and is linked to the vegetation index. And also by having better accurate ABC estimation, we'll be contributing to this above ground biomass, and we want to aim also a proxy towards carbon stocks. Did I jump? Oh, no. Yeah. Well, I won't explain this in detail because Arco will explain a bit later about the data collection and protocols. But yeah, basically, that was the data processing. This is where my work starts, the reference data. So this is mostly the workflow on how to annotate the data and exploit the spatial and spectral information from the RGB and multispectral data for the posteriori deep learning modeling. So what we do is we take the whole orthomosaic image that we have from the previous process step, and we tile it. Otherwise, your computer will explode if you don't go by tiles. In our case, we use grid interregional tiles, 250 by 250. You can use other size if you want, like 512. In order to speed up my annotation, I've been exploring SAM algorithms, that's from Meta AI, and you could install in QGIS or ArcGIS, wherever you like. So that will kind of generate object mask from the input, and yeah, you get this binary mask, and then you can have another experiment to do, but this is the first process. Then you have this GeoJSON format that you feed into the model. But mostly we're going to use rasters. So your predictors, that is 5 channels, RGB plus, we're going to add, wait, can I go back? Yeah. Well, I can show the, I don't know why it's not showing the, what it should be displayed. Sorry. Well, anyway, this was another image that overlap RGB and multispectral data. It's not showing there. But basically what we try is we stack the bands, the RGB data to the multispectral data. We use the standard RGB CNN approach just by using the raw data instead of calculating all of these spectral index that, I don't know, for example, MSAVI that will help to distinguish between the bare earth. But we skip that, and we use the whole multispectral data. And we use it as predictors. So we use this tensor. Tensor is just another denomination, another data structure that is similar to arrays, but it's just a special data structure that you use for deep learning algorithms. So use these 250 by 250 channels layers. We have 5 in our case, and we use those mask tensor that multiply by the classes that you want to predict. Then we have our model. So basically, we're using this CNN architecture based on semantic segmentation because they're pretty good to learn from spatial features, as I mentioned before, the edges, corners, texture that they describe the target class. So basically, it has an encoder and decoder structure that enables the semantic information with high detail of information to maintain the spatial context and spectral information that we're using to deploy a better accuracy of the feature map. So we use the encode where we receive the input image, and we extract the multiple features by using this combinational layer that we put 7, and then a max pooling that reduces the image. That's a mathematical process. Just reduce a 2x2 matrix, grab the highest value of that grid, and then you decode again, and upsample, increase the dimension of the image again, but a process called skip connection. And as a result, you have this output mask that is a cemented mask, like how likely is that pixel to come from those classes? They're pretty good. You don't need much training data. OK. I'll go quick. Yeah, that's the last, structure identification of a 3D structural component. I will use Voxel models as a raster, so just another layer to that tensor for predicting tree shrub grasses. So you just add the height. So we aim to build transferable Australian model ecosystem to establish this ecological information, but just designing a workflow in a way that is modular. So we want to assess terrestrial ecosystems that are prone to climate global change and help to make decision-making and automating this feature extraction of ecosystem information block for analysis. And yeah, well, this is the last function. Just if we haven't reached with multi-spoke data to differentiate between MPV and PV, we will use hyperspectral data, or just like a study of plant trait that are related with woody fraction and senet. It just would be a regression modeling in deep learning. Yeah, that's it. Conclusion, design a workflow that is modular, build transferable Australian automated ecosystem model, and establish ecological information from diverse spatial spectral resolution from the data for ecosystem science. As I said, interpret data you must. And thank you.
Oops, where's the remote? Sorry. Good morning. Thanks for having me back. Okay, so this is the overview of what I'm going to be talking about this morning. Just a quick background of what ET partitioning is. A lot of you would be very well versed about how to do that, but I'd like to concentrate on the T component, which is the transpiration component of the ET, and then drill down on some of the, basic improvements that that we've been exploring to look at self-flow techniques and some key considerations, and then present a couple of slides about scaling up. Okay, so you know the different components of the evapotranspiration. We have evaporation from the soil, evaporation from interception that's captured by the canopy, and then transpiration or water that's being converted into vapor through the process of transpiration. Okay, so I'm just going to grab my cheat sheet here. So the justification for measuring ET and obtaining granular information into its components stems from two main streams. In any terrestrial ecosystem, it is a no-brainer that evapotranspiration is a key component of water cycle. It's also been known that water-limited ecosystems, evapotranspiration may account for more than 90% of the water balance. And quite less obvious, but very important nonetheless, is the role of ET that plays in better simulating water and energy balance. Global economies also rely on the understanding of ET and ET partitioning as agriculture production areas are pushed towards better and higher yields or crop yields, but not to the detriment of the environment. Cropping systems are encouraged to diversify, and critical buffer zones that promote native ecosystems become very relevant. The accurate estimation and to a higher degree measurement of transpiration, evaporation in agri-ecosystem is becoming more imperative in reducing cost, increasing profit margins, and ensuring that finite water resource is judiciously managed. Understanding that different components of the ET are as equally important, please allow me to focus our attention to transpiration or on transpiration. We all acknowledge the huge role that plants make in mediating evapotranspiration. The T to ET ratio will theoretically increase in ecosystems with very high leaf area index, and this is evidenced by a work by Nelson and his colleagues in 2020. The coupling of T with carbon flux is also unavoidable. So this is another, I guess, graph that's familiar to you that I presented yesterday. Measuring transpiration, especially in broad scales, for instance, in an ecosystem is complex. For instance, we briefly demonstrated this in a 50 by 50 meter plot in Fletcher View. And the complexity arises from, and I quote, heterogeneities in physical and physiological properties and processes of plant water uptake. That's again by Nelson in 2020. So accurate ground-based transpiration observations become highly imperative. The next slide will then talk about a tree and stand level measurement of transpiration. So the most common technique to measure sap flow in forest, trees, crops, and other plants are displayed in this slide. So this is, okay, so from Kuhl and his colleagues, published in Agricultural and Forest Meteorology in 2014. Across the body of literature, and because these techniques have been around for many decades, they seem to be the ones that scientists have become most familiar with and confident in using primarily for upscaling transpiration across landscapes, ecosystems, and now more ambitiously in global scales. But what do we need to consider in applying or employing sap flow techniques? Okay, so in all works involving measurement of transpiration, evidences have been shown and described related to sap velocity and tree-level transpiration as affected by variability of xylem sap thickness in the cardinal directions and in terms of radial sap velocity profile. So in Adelaide, where I live, there was a log that was cut, so I took a photograph, and this clearly shows, variability of sapwood, and that's the whitish region or yellowish region just after the inner bark and the cambium layer. So that's more or less like the whitish region there, for those who are not familiar with the anatomy of wood. Variability of sapwood thickness, a predominant characteristic of trees in natural forest stands, will have repercussions in basal sapwood area calculations used in scaling up stand transpiration. So assuming that the sap velocity is constant radially in the sapwood xylem must be avoided. So these are some of the, key things that that we need to consider. So the image on the right is, a proof that, in different species would have different sap flow profile. So the one on top is from a tropical tree called durian, and the other one is, the one below it is a typical eucalyptus tree. Okay, so the next one would be wounding. Okay, so we drill a hole onto a tree to install the sap flow sensor, but care must be done to consider the wounding. And so in this graph, so you have, nice pattern of sap velocities across time, but someone found out that it looks like the signal is becoming weaker towards, a couple of months. And true enough, when they reinstalled the sensors, the signals picked up again. And so this was evidenced by, when after drilling, the wounding has become larger, and so the signal has weakened, and so the sensor is not able to pick up that signal quite easily. Okay, so this is an image that I took of a vine tree or a vine, grapevine in South Australia. So you see the wounding there, and you can also see the pronounced wounding on the heater. The one that's in the middle is for the heater. So as you introduce heat, wounding becomes more, will progressively develop, and so that would affect your signal. So as much as you'd like to be careful in drilling, then other factors like introduction of heat would also impact your measurement. And then longevity of installation. Some species would allow you to have good signals all throughout the season, but some trees are very vulnerable to, say, simple drilling, or even if you try and drill the holes very slowly, reducing the impact of wounding, wounds would still develop in some of those tissues. And so you've got to understand how soon or how long will your signals be, will last. So here you've got February of 2020, and then in the same tree, the following year, you got weaker signal for your flow sensor. So this will provide you some signal that in less than a year you need to reinstall or revisit your site and reconsider reinstallation. Okay, next one is very basic, probe insulation. So some of us might, or some research have been done wherein insulation has not been considered, but this can be, this has profound effect on signals, on data signals. So this is on the same tree. Signal on the left, on your left is prior to when the sensor was insulated, and after insulation you have a better signal to the right. Okay, and then last one would be remote access. So we would like to have good remote access because that gives us flexibility in terms of being able to check validity of data as well as validity of our installation. So having access, remote access to our data, and now we have a lot of communications options available for us, and having that ability to access remote data is really gold. All right, so moving up to scaling. Okay, so I've pilfered this from another scientist, published in 2011, but this gives us an overview of some of the considerations that we need to think about when we're scaling up. So from leaf level to whole tree to forest stands, and then to ecological, to watershed scale. So wouldn't go into much detail into that. It's in this publication, but basically this more or less gives us an idea, as well as, I guess, gives us some direction into forming the right protocol for scaling up. So measurement of transpiration is usually done on a plot scale with representative tree-level transpiration. Achieving high level of granularity in stand or ecosystem-level transpiration may be achieved by appropriately scaling first to the plot level. This is what I observed in most of my readings. For instance, Buckley and colleagues use plot-level allometric estimation of basal area. and demonstrated that greater sapwood area index in the regrowth stand compared to mature stand can explain difference in water use. So regrowth stand use about 120% more than the mature stand. Tree level water use and tree DBH also has a nonlinear relationship. This was found out by Carter Berry. And in scaling up tree water use through an investigation in tropical montane forest, they suggest a careful look at how DBH distribution can have an effect on sap velocity and sapwood depth. All right, so in summary, we can do a little bit of suggestion on improving sap flow techniques, and scaling up must consider ecological and hydrological controls of water fluxes. Thank you very much.
I would like to begin by acknowledging the Ngunnawal and Ngambri people who are the traditional owners of the lands where I live. In this presentation, I'll be talking about improving the accuracy and utility of the habitat condition assessment system for monitoring ecosystem condition using satellite remote sensing. A key concern nationally and internationally is the ongoing decline in biodiversity despite considerable efforts by governments. While there are many ways in which biodiversity can be measured and monitored, we need to complement efforts with methods that can integrate across diverse types of data to provide an overview for consistent national reporting. In this presentation, I'll be talking about the Habitat Condition Assessment System, HCAS, as a way to monitor ecosystem condition or habitat condition using satellite remote. HCAS is a general framework for monitoring habitat condition across entire regions or continents using satellite remote sensing and site reference data for reporting on the capacity of habitats to support regional biodiversity persistence. Reference ecosystems are representative locations where ecosystems have high integrity, that is, places where they maintain characteristic species composition, structure, functioning, and self-organization over time within a natural range of variability. In HCAS, reference sites are used with environmental covariates and remote sensing data to model and predict reference patterns of ecosystems, thereby simulating the variety of Australian ecosystems based on their remote sensing characteristics. The condition benchmarking algorithm then uses predicted and observed remote sensing characteristics of ecosystems and representative reference sites to benchmark condition for each location based on a dynamic model of the departure from high ecosystem integrity reference states. We then apply a calibration algorithm to scale the output between 0 and 1. In this way, we are able to consistently map and assess condition across whole landscapes and continent-wide. HCAS was developed to address three key challenges when monitoring habitat condition using remote sensing: that of context dependency, multiple reference states, and seasonal dynamics. The first challenge relates to making the correct ecological interpretation of land cover. Different locations that apparently exhibit the same remote sensing signal may actually have very different conditions from a biodiversity perspective if modified from their natural state. The second challenge relates to the natural existence of multiple ecosystem reference states over the long term, multi-decadal or longer. Reference states can exist in any of their multiple natural expressions due to spatial variation in the timing and extent of natural disturbance regimes such as fire, even when abiotic environments are very similar. Hence, quite different looking ecosystems from a remote sensing perspective will be associated with the same condition levels. The third challenge relates to the short-term or seasonal dynamics, including within-year and decadal climate cycles. Natural systems exhibit temporal dynamics that do not affect their condition, such as deciduousness or seasonal dieback. The general framework aims to tackle each of these challenges for a correct interpretation of ecosystem condition. This requires a long-term view of remote sensing data sufficient to encompass natural disturbance recovery cycles in order to clearly distinguish natural from anthropogenic influences. The HCAS method is also designed to address a fourth challenge in monitoring habitat condition from space, that of scarce, high-integrity ecosystem reference data especially in transformed landscapes. The HCAS predictive framework enables gaps to be filled by interpolation and multiple reference sites for dynamic benchmarking. HCAS has been developed over a series of projects since 2012. These reports capture the methods and provide recommendations for further work. Version 1 in 2013 was the proof of concept. Then since 2015, in partnership with the Australian Government, we developed version Series 2 and published version 2.1 data. Earlier in 2016, we published a journal paper based on the version 1 proof of concept, and we are currently working on an update based on version 2. The current outputs from Series 2 represent a minimum viable product for national reporting. Limitations mainly relate to accuracy, resolution, and completeness of the three inputs: reference sites, remote sensing variables, and environmental covariates. Using MODIS remote sensing, applications have been limited to 250 metres. As MODIS has reached its end of life, we need to move to a different platform with a long time series such as Landsat. Further, fractional cover variables derived from MODIS mainly detect bare ground and vegetation cover. Aquatic ecosystems are not well characterised, leading to erroneous estimates. End users are also looking for repeated assessments, ideally annual, and much finer resolution for local applications. Going forward, we need to focus on reference sites. HCAS assumes reference sites maintain that status for the duration of the remote sensing assessment period. If that is not true, errors may compound, as reference sites are used in both training and benchmarking the model. Recording temporal information about the status of a reference site will enable correct selections for a particular temporal assessment window. Other critical areas of improvement include uncertainty quantification, to enable a confidence interval to be associated with the condition score. Trend quantification is also of interest to distinguish gradual versus abrupt changes across a time series beyond simple trend lines. And of course, the holy grail is change attribution, understanding causal pathways related to an increase or decrease in condition at a particular location. We have considered all of these requirements and identified pathways forward in our recommendations. As an aside, here's an example of how condition assessments can be summarised, which we developed for a pilot ecosystem account in the Flinders, Norman and Gilbert river catchments of Queensland. Using annual ecosystem condition epochs over 18 years, we applied simple linear regression to assess trend as the slope coefficient and its significance, including temporal autocorrelation. The results can be mapped and tabulated, for example, by ecosystem types, with increases defined where the slope coefficient is positive and decreases where it is negative. Summing across spatial extents and time series provides an estimate of the amount of change that has occurred across an entire region. Cassandra Malley presented other examples of Commonwealth Government uses of HCAS in session 2 yesterday, and there is a poster. We are now embarking on the next phase of work in partnership with the Australian Government. This will be Series version 3. It represents an entirely new development at 90 metres, but it won't deliver on all enhancements and recommendations outlined in the Series 2 reports in the first instance. However, it is a substantial uplift to deliver a more useful product at 90 metres and to extend applicability by addressing issues at the aquatic-terrestrial interface. The primary focus is on the three inputs: reference sites, remote sensing data, and environmental covariates, plus uncertainty quantification and limitations assessment, in order to provide clear guidance for a variety of use cases. National data infrastructures such as TERN and Digital Earth Australia and others are pivotal to these improvements and for an ongoing national condition assessment capability. Achieving such an ongoing capability requires partnerships. It is not feasible for one organisation or one agency to manage all critical data pipelines and modelling infrastructure for regular assessments. In developing the 90-metre instance of HCAS, we are looking toward TERN and Digital Earth Australia, for example, as ongoing providers of data pipelines. I'll next outline where TERN infrastructure is pivotal to these improvements and an infrastructure gap that needs filling. First, we are grateful to TERN for compiling 90-metre environmental covariates to support digital soil attribute mapping, as these are central to a HCAS build at 90 metres too. HCAS uses environmental covariates to model and predict reference characteristics of ecosystems. These need to encompass climates, soils, landforms, and surface hydrology as key drivers of variation in ecosystem types continent-wide. Covariates should reflect pre-1750 variability for predicting remote sensing characteristics of reference ecosystems. However, to model soil attributes, vegetation influences on soil formation also need to be included, and remote sensing variables have been used as a proxy. The resulting predicted soil attributes carry a signature of land use, which can introduce error in the HCAS model. To facilitate HCAS and other work on biodiversity measurement, TERN is developing a new suite of soil attributes that align with input requirements. Here is a preliminary output for soil organic carbon, courtesy of Ross Soil. On the left is the current soil and landscape grid of Australia product, and on the right, using environmental covariates that minimise the land use signature. Ross and his team are presently working on a first version of the pre-1750 digital soil attributes. This new product is relevant to a wide range of ecological modelers whose work requires environmental covariates that minimise the signature of present-day land use. Sites are a critical infrastructure gap. They are needed not just for HCAS but for other applications in ecology or soil science aimed at monitoring and assessing ecosystem health. At present, HCAS infers reference sites from multiple lines of evidence in a static way to come up with a map as shown here. For the new build at 90 metres, we need to retain temporal as well as spatial information for greater flexibility in how we use the data. I've listed a few questions here, and there are many others to consider. How we identify, attribute, database and track reference sites will become increasingly important, especially as we move toward market instruments to incentivise environmental stewardship. Depending on what the use case is, a site may have an intact canopy in a reference state, but a modified understory or vice versa, and still be relevant to use. A site may cover from previous modifications to attain reference status. Field verified sites alone won't be enough for assessment models like HCAS. How can experts contribute, and is there a role for citizen science? Addressing this infrastructure gap requires a national collaborative approach. If you would like to learn more about HCAS, please peruse our project website or get in touch. Thank you for listening. And I also acknowledge the authors from this presentation.
Thank you. We'll have the speakers come out the front. That was an excellent range of talks, and I think it sort of highlights the exciting developments we're seeing in this space of ecosystem monitoring, but also probably the challenges confronted by TERN when you've got all these different sort of things have to be balanced in the understanding of ecosystem trends. So we've got quite a lot of online questions, questions people have submitted. Just start working through them. Andy, question for you. If Australia were to invest in satellite capability, you made the point about the recent de-investment, but what would be the most valuable investment? What should be the priorities?
Microphone's working, yep. Good question. And that is something that is actually, I guess, a scope of work that we need to figure out. So obviously it's a hugely broad subject and area. With it being potentially government investment, it would really be driven by government priorities and how EO data is supporting decisions or work in that space. We've seen a few government programs through this symposium that are driven by and using EO data. So I think that's a starting point, but it's also a gaps in support and capability question, I think.
For Patrick, there's a couple of questions around, I suppose, the ability to expand out ForestGEO. Is there plans to expand the ForestGEO network across other sites in Australia? And linked into that, I think, is can cut down methods be used, and would they be acceptable when, especially in a rich country like Australia?
Right. So the short answer to that is no. There are not plans to extend the plots. Simply just because of the funding at the minute. I think it would be brilliant to do that. We have plots from northeastern China all the way down through Southeast Asia, Borneo, Papua New Guinea, and it sort of stops in eastern Papua New Guinea. We now have the plot in Victoria. It'd be great to have a network of plots up the east coast, with all due respect to my colleagues in the west. But as I think Beryl pointed out in her question, the big issue is cost. So when we did this, we pay, the minimum I can pay students to do the work is $35 an hour. So the plot is the most recent plot in the network. It's also probably the most expensive plot that was ever put in the network. So I think it's usually impolite to talk about costs, but it's probably worth being frank about it. So this plot costs about $400,000 to put in. Probably about $100,000 of that was equipment, so the scanners and the moisture sensors and so on. So it's about $300,000 all up. It depends on many things, so distance to accommodation, availability of people to do the work. In our case, the thing that really was expensive was, if you recall from the map of the plot that I showed, that super dense area right in the middle of the plot, that was probably $100,000 of sampling just on its own, and effectively about an extra 4 or 5 months of work. So it would depend very much on the forest type. So for example, at the site at Waru, that's wide open woodland. That would probably take 2 months to do and would probably be pretty inexpensive. So it would be somewhat context dependent. So I think it would be great to do it. I think there's lots that could be learned from it. But it would be somewhat contingent on making sure you had availability to the funds to do it properly.
So, and to follow on for that, several years ago I visited the Paso site in Malaysia, and one of the issues I was struggling with is how, the ability to remeasure, go out and so how often are these sites getting remeasured?
So the ForestGEO sites are remeasured every 5 years, and to be very clear, the expense is setting up the plot, right? So you have to go, and I think we roughly averaged about 5 people putting their hands on every single tree in the plot. So that's 50,000 trees, that's 250,000 hands-on trees. The remeasurements are pretty quick because every tree's been tagged and painted, so you're effectively going out and identifying if it's still alive, remeasuring the diameter, and that's going to be 98% of the trees. So there'll be a bit of recruitment, and you'll have to put tags on those trees, but you don't have to lay out measuring tapes to do everything. You can just measure distance to neighbors. So it's a fraction of the cost to do the recensus. The real onus is on that initial census, which is quite expensive. And there's a sort of related question of, in Australian context, especially you've got to assume fire is going to be part of the equation. What's the plan in place with if a large scale fire? I saw that question about what's going to happen to the tag when a fire comes through. So it depends. There's 2 kinds of fires that we would be worried about. One is fuel reduction burns. There was a fuel reduction burning was done actually in the plot area about 6 months before we started. We're adjacent to some Melbourne water infrastructure, some aqueducts. We don't expect that the metal tags that we use will be influenced by that, but we're going to go work with Forest Fire Management Victoria and put in just some test tags and wiring and nailing in some of their fuel reduction burns to see what happens. In terms of like a wildfire, a high intensity fire, every tree is mapped, and the sort of errors in our mapping is probably plus or minus about 15 centimeters, and so we know the locations of all the trees. If we have a high intensity wildfire, basically everything that's small is going to be killed, and so it'll be the big trees that are retained, and the errors on their XY measurements are even less. So even if the tags were to melt, we would have a very good sense for where every tree is anyways.
Yeah. Robert, comment, it is a really good tool, I think Beryl pointed out, but is there any plans to link it with the sort of condition assessments that Peter Johnson talked about in his the condition assessment with Peter's strategic conservation analysis, I suppose, from scaling from these property level things to sort of overall regional assessments of the condition and how that impacts on things like the conservation values going forward?
Yeah, it's a good question. There are no, short answer is there are no plans, but pretty much anything's possible if anyone wants to look at other ways of using or interpreting the data. We've got to be careful, obviously, with data privacy, for the purposes it was collected, but in terms of higher level analyses and try and look at other uses of it, certainly. There has been some interest in the past from parks regarding it as a method for just quick sort of assessments. Again, just getting snapshots of condition.
And it's a sort of opt-in process, isn't it? So how do you deal with the issue of maybe the worst land managers may not be doing the condition assessments?
At the moment, because it's on a Esri platform, Survey 123 platform, at the moment we're limited to people that hold an ArcGIS licence. So all of the NRMs, a lot of government staff, delivery partners in the reef space. There are a lot of landholders that want access. And yes, usually it's those that are more motivated, I suppose. But the aim is to have it more widely available, whether it's through, I've been able to negotiate with Esri a bunch of licences to give landholders access, whether it's through that or building a standalone app. We're looking at those issues, but there's pros and cons with where it is now versus standalone apps.
Question for Dr. Park. What is the quantum sensor on the supersite tower? I think there must have been something labelled as a quantum sensor, was it?
Actually, we are more interested in the carbon absorption. So that is related to photosynthesis radiation, quantum sense.
Yeah. Okay. Do you think there'll be an Asian continental EON, Earth Observation Network, like Europe's gone with ALTA or the NEON system in the US? Is that sort of where you think this is heading?
Yeah. We visited NEON last year, and we will benchmark NEON and TERN systems. We need more discussion, maybe.
Yeah. I think that's one of the strengths of these, getting these sort of regional networks to link into global. I think one thing the climate science debate has shown us, a lot of these issues are global and need to be looked at in a global context, not just at a country or even a regional level. Just going back, I've probably missed a couple. What are the habitat traits per species in the plots for ForestGEO? Or are they available? Can you go and find out what the...
So I'm not quite sure the question. So we have identified effectively sort of habitat types based on topography and topographic wetness index, and we have all of that information is certainly available. We have a student who's in the process of collecting functional trait data for the species that are in the plot, and so there's certainly scope to look at the combination of those two things.
Okay. And a question for, well, I think it's for, there's a few people involved in the Earth observation space, for Andy and Matt especially. EO in Australia involves multiple groups besides CSIRO, GA, BOM. How to engage with diverse stakeholders in a useful way with the calibration and validation infrastructure development and use. I mean, it's an issue how to sort of leverage off all the different users. So,
yeah, I think that's the biggest challenge. There's a lot going on in a lot of different organisations, and something that is always challenging when everyone's doing things differently, to try and set common standards or ways of doing things, or bring everyone together. It's which way do you go? Trying to bring everything in the same picture without fundamentally changing what anyone's doing, I think is a goal. Whether that can work, try and work it through, and then slowly. So I think it's a progress over time thing to get everyone on board in the same room.
Sort of related to that, I think it seems there's, I think a good understanding, and we've seen from the presentations on the need to do that validation and looking for transferability of the models that are built and whatever. Given that sort of very platform dependent, I think Kristen mentioned about, Landsat. I think we've got 50 years now or over of Landsat data. How much sort of hindcasting can we do to sort of see where we've come from as much as sort of where we're going?
Sorry, can you repeat the last bit of that?
How much hindcasting? Can we go backwards in time for?
Yeah, I mean that's a good question. I'm probably not the best person to answer it, and not being an I guess EO science-based person myself. We're kind of in AusCalVal trying to bring it all together, and there are initiatives, I think, within international organisations to try and genericise the way some of these activities are done. I think you mentioned often very specific, or historically have been very specific to satellite missions, or how in how they conduct measurements are conducted. So valuability of historical data sets and figuring how we use that, I think, is not something that I can answer, but good question.
Question for Kristen: will the habitat condition assessment ever be final, in inverted commas, or you'll be always revisioning going forward? And I suppose the other thing, if you are, because you do need to make changes, how do you sort of keep a temporal sort of integrity to it all, so we can actually understand the broader trends?
A couple of answers in that. Well, certainly HCAS is on a continuous improvement track, and we're our next build, we're aiming for 90 metres, but we do have a vision for getting it down to about 30 metres. But how we improve it is very much linked to improvements in the three inputs, which are the reference sites, the environmental covariates, and the remote sensing variables. So each of those need to be, confident at the particular scale that we operate at. And critical to that also is the reference sites, which I focused on in my talk in this instance, where we need a lot more work to verify, identify and verify those sites. I'm aware that TERN is starting to build some 30-metre environmental covariates, and so it might be possible, to do something there. But with the remote sensing variables, obviously we need a long-term, to work with. As we move down to 30 metres, we need to also be able to impute values or blend from other sources to reduce the gaps in the seasonality. And at the moment, the current published version of HCAS only has a few sort of longer epochs, but we have developed annual epochs. And we've improved the process by which we develop those annual epochs to give us a sense of condition over time. So it's fairly early days in this journey to develop, if you like, to develop solutions to the challenges that I outlined. There's sort of 4 challenges around how we use remote sensing for condition assessment for biodiversity. So I think we look for continuous improvement. We'll have version control, release versions, documentation around what the changes have been, and assessments around the limitations. So I think going forward, uncertainty quantification is going to be critical, so people can get a sense of how to use it for their particular, case.
Question for Zach. You're in a very challenging environment. How do you ensure the resilience of the kit rather than having to relocate or
Yeah, no, that's a really good question. We actually had some issues with a bit of the kit this last winter. I think the key thing is to talk to people who have done work in the Northern Hemisphere, where there actually is a lot more snow. The key is just avoiding putting equipment where there's major snow drifts. Yeah, we discovered a thing called snow creep, where basically even on a small, gentle slope, snow can kind of move in a glacier-like fashion and literally just bend and break metal. So we discovered that kind of the hard way. So the key we've found is to locate equipment out of deep snowpacks.
A question of Beng, I think of, AusSap FluxNet, what is needed to make it happen. I suppose, how do we integrate a broader understanding of ET type stuff into a broader monitoring of changes in the fluxes and things like that in the water balance, etc.
No, that's a very good question. Plus, I guess there's a deeper challenge for all of us here in this room, especially for TERN. How do we make use, and I've given a challenge yesterday as well in terms of people using sap flow measurements or start to build data for sap flow measurement to capture transpiration of trees and plant species across many landscapes. And so with ICT, we continue to, I guess, look at various directions. How do we push data from the sensor to the logger, and then so that it can be remotely accessed. So we have options, as I said, for either LoRaWAN communications or for Cat-M1 communications. And so we've got capability within the company, and we can assist in that direction as well, but also being able to make different sensors talk to each other and deliver that data to one repository, and then start churning, analyses and more insights into the data that we capture. The model that I see from FluxNet is that they basically capture all existing data set from various researchers across, I suppose, basically from Europe. We can also do that here in Australia, and we need to begin to do that. With that in mind, we can look at many data capture activities that have been done in the past. Plus, we can look at many more upcoming, data capturing that's going to happen in the future. We've been collaborating with many, not only scientists from the academy, but also from the private sector, who are starting to use sap flow sensors in their production systems. So we can basically coalesce together. We can start to dialogue and start sharing data.
With Laura, your data you're using for your studies now, the drone stuff you're collecting yourself, I gather, but are you dependent on other data sources for?
Is it work? Yeah. The data comes from TERN, mostly from Camp Perry Station that we went last year. We brought a whole team with UDAS, with Purnima Arco, and with TERN with Ben Sparrow and others. That was the question. But also for the transferability of the model.
Yeah. So where can it go?
I'm not sure yet, but we did data collection. There is other 10 sites in Tasmania. Probably we'll keep building up the model, but getting data from Tasmania, which is also cheaper because we're already there. I think next year we might go again and get more data. But in my case, I'm not targeting temporal. It's mostly using all these new data analyses to speed up work.
So follow-up, it seems to me we've been on a journey with a lot of instrumentation of camera traps and things like that on standardisation. Is the drone, where's the drone data collection in that space? Is it getting to a standardised thing, or people just going out and doing something new every time?
There is already is available 10 data protocols on the website. So if you want to follow the same data processing and data collection, you can jump on the website, and it's pretty well explained, and there is a few guidelines from how to collect the data, how to use the sensor, how to put all the settings, and even there is some Python scripts for if you into 3D modeling for any software processing. You can go manually or use the advantage of scripts that will give you the outputs that I think it kind of overlap RGB and multispectral data and give you those two orthomosaic images for each site. That is the one I'm basing all my this work on the PhD.
Question for Kristen online. Are reference sites stratified by management and disturbance history?
That's a really good question. So thank you for the questioner. For the training, the HCAS model, remember it's a two-part model, training a reference ecosystem model. The reference sites for that work are stratified and sampled representatively by environmental heterogeneity. For the benchmarking component of the model, we aim to additionally stratify the reference sites by the variability in the remote sensing variables themselves, and that becomes a proxy, if you like, for the natural disturbance regimes. And we do that because we expect multiple reference states due to natural processes of disturbance recovery type responses. We presently only use reference sites for high integrity areas. So we aim to minimise the effects of land use or management history. But we additionally use high intensity land use areas along with the high integrity reference sites to scale the model between 0 and 1. And so recognising that what we're actually measuring is the departure from reference of high integrity in the first instance for the model. So hopefully that answers that question.
And I suppose a follow-up to that is there's been a lot of talk recently about things like the permanence of areas set aside for habitat, for biodiversity protection, whatever. Do you think the techniques you're developing will actually be able to provide that sort of governance of those systems to make sure we're not sort of paying for stuff that actually doesn't deliver biodiversity outcomes?
I mean, I think there's a contribution this work can make, and in highlighting the importance of reference sites in my talk is the recognition that any process of understanding how well areas are starting to improve in terms of their capacity of the habitat to provide for biodiversity, we need a sense of what the reference sites are like and what we're aiming for. There is, obviously we're not trying to restore things as they were because there is change in the process. But so I think it can provide some information to support some decisions, but it's only one piece of the puzzle. There's lots of other sources of information, as one of our presenters gave, that can be used to support decisions.
Okay, thanks. We're running up against lunch now, so there's some questions we didn't quite. There's quite a lot of questions. If you wanted to follow up with the speakers, so if everyone can join me in thanking all the speakers for such a great run of talks.
Thanks, everyone. I'm sorry that we have to stop the formal questions, but they will, of course, continue enthusiastically through the lunch break. So we do have lunch break until 1:30. So please, go enjoy.